Welcome back to Chapter 17, where we're looking at taking more information about equilibrium and acid-base reactions and really just taking it one step further. In our last video, we looked at buffers, and in today's video, we're going to start looking at titrations, specifically titrations dealing with pH. So this is a little bit different from what we did in Chem 1 with colored indicators. So just as a reminder, what is a titration? The whole purpose of a titration is to solve for a concentration of a substance that is unknown. So most of the time when people are doing titrations, it's either an acid-base neutralization reaction or it's an oxidation reduction reaction. And so you know what substances you have, you're trying to find the concentration of one. But a pH titration is also useful in determining what kind of weak acid or weak base you are using in the titration. So if you have an unknown compound, a titration can be useful as well. We're just going to be looking at acid-base titrations, and we're going to be looking at a pH titration curve. And so this is specifically the pH versus the titrant. And so it's going to look something like this, where we have pH on our y-axis, the volume on the x-axis, and it creates what we call an S-curve. So it looks something like this. And the point right in the middle of it, right here, is what we call the equivalence point, also known as the stoichiometric point. Means the same thing. This is where we have moles of acid equal to moles of base. So when we say stoichiometrically equivalent, we mean moles. So our moles of acid and base are equal to each other. Now, what exactly is a titrant? Well, a titrant is the solution being added from the burette. So recall, the burette is one of those long, thin pieces of glassware that we can use in order to accurately and precisely add in solution into another vessel. The analyte is the name of the other solution that we're using, and so the analyte is what the titrant is added to. Most of the time, the analyte is our unknown. That's what we're looking for. So in this chapter, we're going to look at strong acid and strong base titrations, strong acid and weak base titrations, and strong base weak acid titrations. So we're going to start off just by looking at strong acid, strong base. And here are the two possible curves that we could end up seeing. So for this first curve on the left, we can see that it starts at a very low, a very acidic pH. And so usually your pH probe is in your flask. It's not in your burette. So that means that in the flask, we have acid. So our analyte in this particular instance is an acid. Whereas you can see that over time, we're adding sodium hydroxide and we end up getting a basic pH. So our titrant here is the base. On the other side, on the right side, you can see that we're starting at a very basic pH. So here our analyte is base and our titrant is acid. Now, one thing that I do want to point out to you is where or how we can find the equivalence point. And the way we find the equivalence point is by looking at where on the graph we see that vertical line. This vertical line is very important. It means that there is a large jump in pH very quickly. And the equivalence point is going to be right in the middle of that vertical line. Again, the equivalence point is going to be right at the middle of that vertical line. So in this case of a strong acid, strong base curve, whether we're looking at the left graph or the right graph, the equivalence point will always be at pH 7. Always. Because when our moles of acid equals our moles of base, we end up just making water and a salt. And that salt, since it comes from strong acids and strong bases, does not play any role on the pH. So that means that we are left with just water, essentially, which is the only thing that's contributing to our pH. And we know that pH of water is 7. So if we look on our other curve, we can see that it's a pH of 7 as well. So what's happening here is we're starting with our acid, right? Eventually we get to a point where our acid and our base are equal to each other. And then all of the acid has been used up. So that's why we end up basic at the end. Whereas if we look at the other one, we start off basic, eventually we get to a point where our acid and base are equal to each other, and then all of our base is used up, so we have just acid left over. And that's why we end up with that S-shaped curve. Now let's look at the different points of a graph where we can determine what the pH is. There are 4 main regions. We can do it before any of our titrant is added. And so for that, the pH of the system is equal to the pH of the analyte. And since this is a strong acid or a strong base, we know how to find the pH of the analyte from chapter 16. We already did that. If we are before the equivalence point has been reached, but some of the titrant has been added, so this is before we hit that equivalence point on our graph, here we can find the pH of the remaining analyte. And I'll show you what that means. But remember, the acid and the base are neutralizing each other. So eventually, all of that base is going to get neutralized and we're just going to have acid left over, or vice versa. At the equivalence point, remember pH is always going to be 7 for a strong acid, strong base titration. And then after the equivalence point, the pH is equal to the pH of the titrant in excess. So we're going to take a look at these different pieces. How can we identify what we're looking at? Are we before the titrant? Are we before equivalence? Are we at equivalence? Or are we after equivalence? And we're going to determine how to find the pH. This is going to require a BCA table. Again, we're using BCA because we're adding solution, which means we're changing our volume. And in us changing volume, we're changing concentration. So we want to use moles, not an ice table. So let's take a look here. In this titration, we have 25 milliliters of a sodium hydroxide solution, and our titrant is HCl. So in our burette is HCl, in our flask we have sodium hydroxide. We want to find the new pH after adding 5 milliliters, adding 25 milliliters, or adding 18.38 milliliters. So I'm going to go over to a blank screen so I have a little bit more space. And let's take a look at this. So we're mixing sodium hydroxide, NaOH, plus HCl. And we said that for a strong acid, strong base reaction, What happens in the product side does not play any role on the pH. So we can actually ignore the products for a strong acid, strong base titration. So we're going to set up our BCA. And remember, we want to be in moles. So our B for sodium hydroxide, we're told that we have 25 milliliters of a 0.25 molar solution. So for NaOH, we have 0.25 molar and 25 milliliters. So we can find our moles, and you should end up with 6.25 times 10 to the negative third, or you could write it as 0.00625. Either way. For our HCl, we're going to start with letter A, which said we are adding 5 milliliters of titrant. So for the HCl, we're told that it is a 0.34 molar solution. We're adding 5 mils. So that is equal to 0.0017 moles. So we can ask ourselves, at what point of the titration are we in? Are we before any titrant has been added? Well, obviously not, because then HCl would be 0. Are we before the equivalence point, or are we at or after the equivalence point? Well, we know we're not at the equivalence point, because if that was the case, then our moles of acid and moles of base would be the same, and they're not. So our moles of HCl are less than our moles of NaOH. So this means that we are after adding some of our titrant, but still before the equivalence point. So we need to find out the pH of the remaining analyte. So remember, we are going to completely neutralize whatever is added. So determine which of those numbers is smaller. In this case, the smaller number is HCl. That means that the A for HCl is going to be 0. So that tells us then that the change has to be 0.0017. So we take 0.00625 minus 0.0017, and we get 0.00455. But we're not done yet, because the question asked for the new pH. Well, now we have our concentration of, or not our concentration, sorry, our moles of base, right? Since we have our moles of base, we know that in order to find pH, we need to be in molarity. We need to be in a concentration. So we have to convert to molarity using the total volume. So our total volume here is 25, our total volume here is 25 plus 5, so that's 30 milliliters. So we have 0.00455 moles divided by 0.030 liters. So our concentration is 1.51. Oops, I missed a 0. Hold on. 0.00455 divided by 0.03. There we go. I thought it looked a little high. So 0.152 molar NaOH. And then we know how to find pH from the concentration of a strong base. So we can start by finding pOH. So that's negative log of 0.152. And that gives us 0.818. So then to find the pH, remember we're going to take 14 minus pOH to find pH. So 14 minus that gives us 13.18 as our final answer. And so that's how we determine the concentration for part A. Now we're going to look at part B. Part B is once we've added 25 milliliters of our titrant. So we're not saying that we're adding 25 more mils. This is a brand new problem. Okay. So everything is going to look the same except for our amount of HCl. So let's erase this. We have our NaOH plus our HCl, BCA. We said that the sodium hydroxide is 0.00625, and we need to find out what the HCl is. So it's still a 0.34 molar solution, but this time we're adding 25 milliliters. So that's going to be 0.0085. So again, we know that we're not at the equivalence point because our moles are not equal to one another. So the one that has less is going to be consumed, which in this case is our sodium hydroxide. So our after is going to become 0 for sodium hydroxide, which tells us that the change is minus 0.00625. So 0.0085 minus 0.00625 gives us 0.0788. And again, we need to convert that into molarity. So we have 0.0788 moles. We added 25 milliliters of sodium hydroxide with 25 milliliters of HCl. So that's 50 milliliters, which is 0.05 liters. And so that gives a molarity of 1.58. Let me just double check that I did that right. Nope, I definitely didn't at all. So, all right, so this number is wrong. 0.0085, something must have happened when I typed it into my calculator. So we're getting 0.00225. Sorry about that. I thought the number looked a little off. So take that divided by our 50 milliliters, and we get 0.045. There we go. That looks much normal. And so this is our concentration of HCl. So now we can find our pH by taking the negative log of our acid and we get 1.35. So for this one, we didn't have to use 14 minus because we were looking at an acid directly. We weren't looking at a base. So that's our part B. And then part C, we still have the same amount of sodium hydroxide. For the hydrochloric acid, it's still a 0.34 solution, but this time we're adding 18.38 milliliters. So that gives me 0.00623. And 623 and 625 are extremely close. So at that point, we would say these two are equal to each other. That means that we are at the equivalence point or the stoichiometric point. So the pH equals 7, and we don't even have to do any more math out of that. And that is how you do a strong acid, strong base titration. So always ask yourself, am I at the equivalence point? Because you don't have to do any extra math if you're at the equivalence point. If you're not at the equivalence point, that's when you have to actually fill in your BCA table. So always determine first, am I at the equivalence point? So let's go back over to the slides. And now we're going to look at what happens if we add a weak acid with a strong base. So let's take a look at this curve. And we can see a couple of factors here. First of all, if we compare this curve with the strong acid, strong base curve, the pH here is very low. It's about 1. If we're dealing with a weak acid, however, we're starting at a higher pH. So that's one indication that you're looking at a weak acid. It starts at a slightly higher pH. It's still acidic, but it's not very, very low. However, we still end up with a very high pH, so that tells us it's a strong base. Another factor that we need to look at is if we look back at our strong one, we can see that it remains from here to here relatively level or relatively stable in pH. It really only changes by about 1 pH. But if we go to our weak acid base, it starts at about a pH 2 and it goes up to about a pH of 5 or 6. So that's a much bigger range that we're traveling up before we get to our equivalence point. This region is called the buffer region. Because at this point, you've added strong base to create the conjugate base of the weak acid. So now we have a weak acid and its conjugate base, which is a buffer. So we're creating a buffer at that point. Then same thing, we look in between our vertical line and look for right in the middle. That's our equivalence point. So notice that here, our equivalence point for a weak acid and a strong base curve is going to be slightly basic. So for this particular graph, we can see that it's at about 8 pH, so slightly basic. Again, this is because at the equivalence point, we have equal moles of acid and base. So that means that those don't exist. They completely neutralize each other. So all that we have left is water and the conjugate base. And the conjugate base is going to be slightly basic because it's the conjugate of a weak acid. So our equivalence point is slightly basic there. Okay. So in this particular graph, we can see that the analyte is the acid because it's starting with an acidic pH, and the titrant is our strong base. So again, just like with a strong acid, strong base curve, we can look at the 4 different places for us to find the pH. The first is before any of the titrant, in this case it's going to be the base, is added. And so in order for us to do that, the pH is equal to the pH of the weak acid. Again, we looked at how to find the pH of a weak acid in chapter 16. So this is one of those cases where you'll have to do an ice table. And remember, you're looking for the equivalence concentration of the H3O+. Then we can look at before the stoichiometric point, but after we've added some of our titrant. And remember, this is our buffer region. So to find the pH, we find the pH of the buffer. And in order to do that, you're going to use the HH equation, the Henderson-Hasselbalch equation. So remember, that's pH equals pKa plus log of the concentration of base over the concentration of acid. Then we can look at the stoichiometric point. And so at the stoichiometric point, remember, all that exists that can change or affect the pH is the conjugate salt. So the pH is controlled by excess strong acid. Sorry, not strong acid. pH is controlled by, I'm looking at the wrong thing. The pH is controlled by the salt. Whew. And so since that's the case, it's going to get a little bit crazy. We're actually going to use an ice table and Ka since it's controlled by the salt. Okay, this looks a little crazy. We're going to do an example of it in class. And then after the stoichiometric point, this is the part that I was just talking about. I was getting a little confused. The pH is controlled by the excess strong base. And I wrote the wrong thing here. Instead of the ice table with Ka, you want to use the ice table plus Kb. That's my bad. I'm just looking at the wrong slide. There we go. So at the stoichiometric point, the pH is controlled by the salt. So you're going to use an ice table and Kb because you're looking at the conjugate base. And then if we are at the after the stoichiometric point, you're going to use the excess strong base to determine the pH. And again, we know how to find the pH of a strong base. And so we'll look at an actual problem like that in class since we are out of time. And then we'll look at weak base strong acid titrations at the end of class.